Greetings and good time of day to you. I've been sent this Hitachi HA-4800 integrated amplifier for repair. From the outside at least, it looks very similar to the HA-4700 you might previously have seen me work on. Its owner tells me it produces no audio output and that some of the front panel lights don't work. It seems there's no detailed service information available for this model, but I have found a circuit diagram and some brief accompanying notes, the main gist of which are that this model is based on the HA-4700 and that most of the service information for that model applies here. So before delving inside, let's have a quick look at its circuit diagram to get a feel for the overall design and topology and to see how it compares to the 4700. This is the HA-4700 circuit diagram. The signal inputs are here, along with a set of signal selection switches, the selected signal being sent to the tone control and filter circuits, along with their associated control switches. The output at this stage is fed to the main power amplifier section here. There's a monitoring IC, which checks for various conditions such as excessive current through the output transistors, or excessive DC offset at the output, and if it detects any of these problems, it disconnects the loudspeakers by de-energizing a relay. The power supply consists of a pair of mains transformers feeding a bridge rectifier to produce positive and negative power supply rails. An additional pair of lower voltage power supply rails is generated by a pair of Zener-diode-based regulators, each with its own pass transistor. This is the HA-4800 circuit diagram. Much as before, signal inputs are here, which pass through selection switches and the tone control and filtering circuits, which is all very similar to the previous model. Here's a closer look at the power supply section. This time there's a single mains transformer, but as before it feeds a bridge rectifier to produce plus and minus 43 volt supply rails. A pair of lower voltage plus and minus 24 volt supplies are generated again by Zener-diode based regulators. A potential divider then generates yet another pair of power supply rails of plus and minus 14.5 volts. The same or very similar monitoring IC is also shown here, and exactly as before it checks for various fault conditions, and should they be detected, it de-energizes a relay to disconnect the loudspeakers. Here's the main power amplifier section, and it's where the main differences are. Rather than being an all-discrete design, it uses two block modules, shown here and here. The first is an STK3062. This apparently is its equivalent circuit diagram. I'm slightly surprised to see that this datasheet indicates that this module is able to output 60 to 80 watts into an 8 ohm load. The circuit diagram shown doesn't look quite as I'd expect it to for a power amplifier output stage. However, here it's not used to do that, it's used to provide a voltage gain. The output of it is connected to this second module, which is an STK8250, and again this is apparently its equivalent circuit. This looks much more like a traditional power amplifier stage with doubled up output drivers here and here. I would think that this trim pot here can be used to set the quiescent current through the output transistors. The notes I've got don't say anything about how this should be adjusted, but I imagine setting for the same current as in the HA-4700 would be appropriate. A major difference is that there is no control to adjust the DC offset at the output. Instead, there's a servo mechanism here that samples the output and adjusts one of the inputs to this module to hopefully result in zero DC offset at the output. There are a few transistors over here and here that are used for fault monitoring, and these are connected up in almost exactly the same way as in the 4700. This pair here monitors for excessive current through this emitter resistor. This amplifier has a pair of 0.22 ohm emitter resistors connected to the output transistors just in the same way as the 4700. If too much current is flowing through this resistor, then it pulls away the voltage at the input here to this output stage to reduce that current. This transistor does the same thing for this output resistor, and also when it operates, this transistor here detects that condition and signals that fact to the monitoring IC, which presumably will then disconnect the loudspeakers. Here's the inside. Mains power arrives here and is terminated directly on the circuit board. It's connected via this fuse and the front panel switch to the transformer's primary. As always, I'm not too happy about devices like this that contain uninsulated internal mains wiring and have an all-metal chassis that isn't connected to the mains protective earth. I'm not sure whether present-day safety regulations would allow a device like this to be considered as double insulated. Certainly I think current regulations would require additional insulation over the mains wiring so it's not so easily accessible with the lid removed. However, regardless of the mains wiring, because of the main plus and minus 43 volt power supply rails, it would be very sensible to assume that almost all parts of this device have dangerous voltages present. This caution applies to most audio power amplifiers. Sometimes I've wondered whether it would be worth making a main safety earth connection to the chassis of devices like this. Of course, depending on the nature of the connected audio sources and how they're connected, this can sometimes lead to the pickup of unwanted noise. But if a bit of care is given to how the devices are connected, this problem can usually be avoided. A possible compromise might be to connect the protective earth to the chassis via a resistor. If the value of the resistor is selected carefully, it should avoid the noise problem, but yet might still allow for sufficient current to flow to earth in the case of a fault to blow the fuse, and certainly it would operate an RCD unit. A more advanced option might be to employ a special protection circuit that doesn't connect the earth directly to the chassis under normal circumstances, but monitors for any voltage on the chassis, and if that should appear and be over some threshold, it then directly shunts the chassis to earth, allowing a very large fault current to flow, and so the internal fuse or some external fuse or protective device will operate in exactly the same way as for any other piece of mains-powered equipment with an earthed chassis. However, I'm not going to do that here, but I will check very carefully that all the mains wiring is secure and not touching anything it shouldn't. You can see the two STK8250 power output modules here and here. I suspect these aren't traditional integrated circuits, but rather are built of discrete components and are potted in these large modular blocks. This one has a connected series capacitor and resistor that looks a bit like an afterthought. I don't think that's shown on the circuit diagram, so perhaps it was discovered that this model is rather prone to unwanted oscillations, in the same way as I found for the HA-4700 that I repaired, though I'm not sure why its partner over here doesn't deserve the same treatment. These ceramic packages contain the 0.22 ohm emitter resistors for the output transistors, and the common center point is the right-hand terminal. Here you can just see the top of the STK3062 module. This provides voltage gain for both channels. Down here, this must be the loudspeaker switching relay, and so I assume this single inline package IC right next to it must be the monitoring IC. It's labelled IC901, though this reference isn't shown on the circuit diagram. I've already used an ohmmeter to make some basic checks. I've confirmed the mains input is not short-circuited, neither is it shorted to the chassis. The fuse in the mains plug is good, as is the internal fuse. The primary of the transformer hasn't failed short-circuit nor open-circuit. The front panel main power switch seems to be working correctly, and I couldn't detect any short circuits affecting the main DC power supply rails. I've got the main supply connected, though not yet switched on, via an RCD that should disconnect the supply should it detect an imbalance of more than 10 milliamps or so. So I'll switch the mains on, and I'll prepare to press the front panel switch, And as I do that, I, along with you, will keep a close eye on the loudspeaker relay to see whether its contacts operate, as I believe they should a few seconds after switching the power on. I've pressed the front panel switch, and I note that it hasn't lit up as I suspect it should, but some of the other lights on the front have come on. It doesn't look as if the relay has operated, and I haven't heard it click. The chassis is connected to the 0-volt power supply rail, so I've connected that to the common terminal of this voltmeter. Its other input is connected to this probe, and I can use that to check the voltages on the power supply rails. I should be able to access the main plus and minus 43 volt supplies at the bridge rectifier. It might look as if my hand is very close to the mains connections, but I assure you I'm keeping it well clear. There doesn't seem to be a problem there. I can also check the plus and minus 24 volt supplies, and those should be present on the emitters of these two transistors down here. The emitters are very helpfully labelled on the PCB silkscreen. So it looks as if the power supply sections are working properly. I've configured this signal generator to produce a sine wave of 1 kHz with an amplitude of 1 volt peak to peak. Its output is connected to both channels of the aux input of the amplifier, and I've set the amplifier's front panel controls to make that the selected input. You can also see the output of the signal generator as the lower trace on this oscilloscope. The other channel of the oscilloscope is connected to the output of one of the amplifier's channels. I'll switch the amplifier on now. The oscilloscope shows there's a DC offset on the output of that channel of fairly close to minus 2 volts. I switched the oscilloscope to trigger from channel A, which is the channel connected to the amplifier, and also for AC coupling for that channel. Now I'm turning the time base setting up, and that will hopefully reveal whether or not this amplifier channel is oscillating at a relatively high frequency. This oscilloscope has a bandwidth of 25 MHz, so if the amplifier is oscillating at some frequency much higher than that, I won't detect it. But I can't see any sign of that happening here. I'll now connect channel A to the amplifier's other channel. That too is showing an output offset of relatively close to minus 2 volts. Again, I'll look for any high frequency oscillation there. There doesn't seem to be any. The amplifier's volume control is turned all the way down. Despite that offset, it's possible that if I turn it up, some of the input signal will make its way to the output, so I'll try that now. It seems a very slight sign of the signal appears with the volume control turned all the way up, but clearly something's not right. Let's make sure the test signal is indeed present at the amplifier's input. That's one channel. and the other. Here's the circuit diagram of the input section. We already know the test signal is present over here, so if it makes its way through the selection switching and the volume control, it should also appear at the input to this op-amp here on pin 3 of IC601. And if that op-amp circuit is working properly, it should also appear on its output at pin 6. Here are the two instances of IC601. Of course there are two, one for each channel. I still have the test signal applied, so first of all I'll connect the oscilloscope to pin 3 of one of these, that's its input. And I'll turn the volume control up. There is a signal present there, so let's now have a look on the output of that op-amp, which is on pin 6. There's a slight DC offset, but no sign of the test signal. I turn the volume control all the way up. Next I'm going to test the power supply connections to that op-amp. According to the circuit diagram, it should be connected to the plus and minus 14.5 volt supplies. So if I connect the oscilloscope probe to those, they should deflect the trace right off the display. So first of all, one of the supplies should be connected to pin 7. Nothing, there seems to be no voltage present there. The other power supply voltage should be connected to pin 4, so I'll check that one. That's the same story, so there seems to be a problem with the power supply for this op-amp. I believe I found the likely cause of the problem down here. These two Zener diode controlled transistors generate the plus or minus 24 volt power supply rails. There are then two potential dividers formed of these resistors and these two here that create the plus or minus 14.5 volt power supplies, and those are used by the op-amps. Now, these 220 ohm resistors here are fusible resistors, that is, they're designed to fail open circuit or very high impedance if they're overloaded. With the power on, I measured plus and minus 24 volts on this side of these resistors, but no voltage at all over on this side. The power is now off and has been for a while, and these two probes are connected to the multimeter, which is configured to measure resistance. So if I connect the meter across one of these resistors, you can see that 15 megohms is certainly a very long way from 220 ohms, and I've measured exactly the same for the other. If I leave that probe connected there, which is the output side of this divider, in other words the side that's connected to one of the op-amp's power supply inputs, and connect the other probe to the chassis, that shows about 10 kiloohms, which is the resistance of the other resistor of the divider that goes down to 0 volts. So it doesn't look as if the op-amp or anything else connected to that supply rail is short-circuited. I've done the same for the other resistor with exactly the same result, so it seems those fusible resistors have failed. So the question of course is, have they failed because something has overloaded them, or perhaps this type of fusible resistor is prone to failing due to old age? Certainly I found a number of failed fusible resistors in the HA-4800 that I repaired, and I never was able to work out exactly why they'd failed. While investigating this area of circuit, I've also noticed that this transistor here is rather loose. I don't think it's a good idea to mount components in this type of package without additional support, particularly on a single-sided circuit board like this one. I've never found one that's completely broken off, but certainly sometimes the solder joints break, or in the even worse cases, the tracks on the other side of the circuit board get torn away. These are two new 220 ohm fusible resistors, and I've temporarily connected each in parallel with one of the failed resistors. I've also connected each in a series with an ammeter, so I'll be able to see how much current flows when I turn the power on, which I'll do now. $18 milliamps in each case doesn't seem unreasonable, and I heard a faint click and saw that the relay contacts of the relay that connects the loudspeaker operated, so that's a promising sign. If I bring in another meter, I can check the voltages on the output of these potential dividers. The circuit diagram says they should be plus and minus 14.5 volts, so they seem a little bit out. However, I've checked the value of these resistors, and the voltages at the input of the dividers are about right. So unless something using these power supply rails is drawing insufficient current, then I think this must be how it's supposed to be. I've had a closer look at the circuit diagram, and I believe the op-amp power supplies are supposed to be plus and minus 19.5 volts, not plus and minus 14.5. The scan I've got isn't of very good quality, and the labels are difficult to read. Anyway, I've still got the two new 220 ohm resistors temporarily connected, and I'm using the signal generator to feed the same 1 kHz test signal into the amplifier. You can see that signal in the lower trace on the oscilloscope, and just as before, I've got the other oscilloscope channel connected to one of the amplifier's outputs. This time there's a negligible DC offset on that output, and if I now turn up the volume control, an output signal is present as it ought to be. If I keep turning it up, I want to change the vertical scaling. All the way till the signal begins to clip, which is with the volume control almost all the way up. The vertical scale is now 50 volts per division, and so the signal is clipping at about 90 volts peak to peak. Also, the power indicator bar graphs on the front of the amplifier are both fully illuminated. I turn the volume control back down and move the oscilloscope probe over to the output of the other channel. Hopefully exactly the same will happen there. So still with 50 volts per division on the vertical scale, I now turn the volume control up. And the response is identical. So with a bit of luck, this amplifier might now be fully functioning. So my next step will be to properly fit those new resistors and perform some more thorough tests.